Okay, now I would like to explain the problems on inductance. So first one, if a coil of 800 microhenries is magnetically coupled to another coil of 200 microhenries, the quotient of coupling between two coils 0.05. So find the mutual inductance if two coils are connected in. So first one series aiding, next series opposing, next one parallel aiding, next one parallel opposing. So the mutual inductance between the two coils is given by, so M equals to formula K into root L1 L2. So given K equals to 0.05, L1 equals to 800 microhenries, L2 equals to 200 microhenries. So square root of 800 into 10 to the power of minus 6 into 200 into 10 to the power of minus 6. So finally the mutual inductance value 20 microhenries. So now we have to find the inductance value, equivalent inductance value in different connections. So first one, series aiding connection. In series aiding connection, the equivalent inductance equals to L1 plus L2 plus 2M. Here L1 equals to 800 microhenries, L2 equals to 200 microhenries plus 2 into M. This is the formula in case of series aiding. L equals to L1 plus L2 plus 2M. So by substituting L1, L2 and M values, we get L equivalent value. So 1040 microhenries. So next one, series opposing connection. So series opposing case, the equivalent inductance L equivalent equals to L1 plus L2 minus 2M. So L1 equals to 800 into 10 to the power of minus 6, L2 equals to 200 into 10 to the power of minus 6 minus 2 into M equals to 20 microhenries. So 2 into 10 to the power of minus 6. So finally the equivalent inductance value 960 microhenries. So next one, parallel aiding connection. So formula L equivalent equals to L1 L2 minus M square by L1 plus L2 minus 2M. Okay, substitute L1 L2 and M values. So we get L equivalent equals to 166.25 microhenries. So next, parallel opposing connection. So formula L equivalent equals to L1 L2 minus M square by L1 plus L2 plus 2M. L1 equals to 800 microhenries, L2 equals to 200 microhenries minus M equals to 20 microhenries divided by L1 plus L2 plus 2M equals to 1040 microhenries. So the equivalent inductance value 153.46 microhenries. Okay, next problem. A solenoid with N1 equals to 2000, R1 equals to 2 centimeters, I1 equals to 100 centimeters is concentric within a second coil of N2 equals to 4000, R2 equals to 4 centimeters and I2 equals to 100 centimeters. So find the mutual inductance, assume free space condition. So first here, solenoid case. The solenoid with large length, here length equals to, length is large value, so compared to its cross section. Generally solenoid case, length is large compared to cross section. The magnetic field intensity inside the coil can be assumed to be constant and 0 for points outside the solenoid. In solenoid case, the total magnetic field present inside the magnetic material, that is inside the solenoid, the magnetic field is present. Outside the solenoid, the magnetic flux equals to 0. So let the current flowing through the coil equals to I1. The magnetic field intensity formula, the magnetic field intensity equals to H1 equals to N1 into I1 by L1. So it equals to, so 200 into I1 by L1 equals to 100 centimeters. L1 equals to 100 centimeters, L2 equals to 100 centimeters. Substitute L1 equals to 100 centimeters. So it equals to 2000 into I1 amperes per meters. Okay, these two are lengths, L1 value and L2 value. So next, the flux density is given by, we know that the relation between field intensity and flux density B1 equals to mu into H1. So mu equals to mu naught into mu R. So H1 equals to okay, mu naught into mu R into H1 equals to 4.2 10 to the power of minus 7. Mu naught value 4.2 10 to the power of minus 7 and H1 value 2000 into I1. So it equals to 2.5132 into 10 to the power of 3 into I1 Webers per meter square, B1. So next, flux equals to flux and flux density relation, pi equals to B into A. So pi 1 equals to B1 into A1, B1 equals to this one and A1 equals to pi into R square formula. So r value equals to 2 centimeters. So pi into r square 2 into 10 to the power of minus 2 whole square. So finally pi 1 equals to 3.1582 into 10 to the power of minus 6 into I1 Webers. So next the mutual inductance between the two coils is given by M12, it equals to N2 into pi 1 by I1. N2 into pi 1 by I1, second coil number of turns into flux coil, okay, first coil magnetic flux divided by first coil current. It is mutual inductance. Okay, substitute these values. N2 equals to 4000, pi 1 equals to 3.152 into 10 to the power of minus 6 into I1 divided by I1. So finally the mutual inductance equals to 12.633 millihenries. So if it is self-inductance, if you want to find the self-inductance of the first coil, so L1 equals to N1 pi 1 by I1. By using that formula we can find the first coil self-inductance value. Second coil self-inductance equals to N2 pi 2 by I2. This is mutual inductance. So second coil number of turns into first coil magnetic flux divided by first coil current. It is mutual inductance between first coil to second coil. Okay, next problem. A solenoid of 500 tons has a length of 50 centimeters and the radius of 10 centimeters. A steel rod of circular cross section is fitted in the solenoid coaxially. Relative permeability of steel is 3000. A DC current of 10 ampere is passed through solenoid. So find the inductance of the system. First one. Second one, the energy stored in the system. Third one, the mean flux density inside the solenoid. So first given data, number of turns equals to 500, length of the solenoid equals to 50 centimeters. So 50 into 10 to the power of minus 2 meters. R equals to 10 centimeters. So it equals to 10 into 10 to the power of minus 2 meters, or it equals to 0.1 meters. Next given steel relative permeability 3000 and current equals to 10 amperes. So first one, magnetic field intensity formula. We know that the magnetic field intensity equals to H. It equals to Ni by L, ampere turns per meters. Next the magnetic flux density. So B equals to formula mu into H. So it equals to mu naught into mu R, Ni by L, Webers per meter square. So next the magnetic flux formula. Magnetic flux pi equals to B into A. B equals to this one into A. So here A equals to pi R square. So finally pi equals to mu naught into mu R, Ni by L into pi R square Webers. So first one, inductance of the system. The inductance formula L equals to N pi by I. So it equals to N by I and pi equals to, okay, pi formula mu naught into mu R, N into I by L into pi R square. Okay, this is the pi formula. And final equation mu naught into mu R, N square pi R square by L. So next to substitute values. First one, mu naught equals to 4.2 10 to the power of minus 7. So given the relative permeability equals to 3000, number of turns equals to 500 square into pi, R value equals to 10 centimeters or 0.1 meters, 0.1 square divided by L. L equals to 0.5. So finally the inductance value 59.2176 henries. So next one, the energy stored in the system. So the energy stored in magnetic field equals to formula half Li square. So it equals to half into L value 59.2176, current value given 10 amperes, 10 square. So finally the energy stored equals to 2.96 kilojoules. So next one, the flux density inside the solenoid. So already we derived expression B equals to mu naught into mu R, Ni by L. So by using this formula we can find the flux density. So B equals to formula mu naught into mu R, Ni by L. Mu naught equals to 4.2 10 to the power of minus 7. Mu R equals to 3000. N equals to 500, I equals to 10 divided by 0.5. So finally the flux density equals to 37.69 Webers per meter square. Okay, next problem. So two long straight parallel wires in air 2 meters apart carrying currents I1 and I2 in same direction. The field intensity H at midpoint equals to 7.5 ampere turns per meters. If the force on each wire per unit length is 2.5 into 10 to the power of minus 4 newtons, determine the currents I1 and I2. So first given values, okay, the distance between the conductors equals to 2 meters and first conductor current I1, second conductor current I2. So both are flowing in same direction. The magnetic field intensity at midpoint equals to 7.5 ampere turns per meters, and the force per unit length equals to 2.5 into 10 to the power of -4. So find the currents I1 and I2. So first we know that the magnetic field intensity due to line conductor H bar equals to formula I by 2 pi r into A pi bar. Here first one, the magnetic field intensity due to long wire 1 is given by H1 bar, it equals to I1 by 2 pi r into A pi bar, where r is the distance of midpoint from the wire 1. So r is the distance between wire to midpoint. So similarly H bar due to long wire 2 is given by H2 bar, it equals to I2 by 2 pi r into A pi bar. So here H2 bar in opposite direction as compared with H1. So H bar equals to I1 by 2 pi r into A pi bar minus I2 by 2 pi r into A pi bar, it equals to 1 by 2 pi r into I1 minus I2 into A pi bar. Okay. So if we find the magnetic flux direction between the conductors by applying right hand thumb rule, the magnetic flux between the conductors are opposite direction. So that's why here the resultant magnetic field intensity equals to H1 minus H2. H1 minus H2. So first one H1 and it is H2. So finally this is total magnetic field intensity expression. But in problem they given the magnetic field intensity at midpoint equals to 7.5 ampere turns per meters. So 7.5 into A pi bar equals to total magnetic field intensity I by 2 pi r into I1 minus 1 by 2 pi r into I1 minus I2 into A pi bar, and finally I1 minus I2 equals to 47.12. Okay, let it is equation number 1. So next one, okay, given the force per unit length equals to 2.5 into 10 to the power of -4. The force per unit length formula F by L equals to mu into I1 I2 by 2 pi d. Okay, by substituting values we get I1 into I2 equals to 2.5 into 10 to the power of 3. So next, by using these two equations, I1 minus I2 equation, I1 into I2 equation, we can find I1 value and I2 values. Here I1 equals to 78.75 amperes and I2 equals to 31.66 amperes.